Hey, welcome back to another video with Rosalind Carson. Today we're going to derive all the trig identities that are generally taught in a high school trig course. And we're just going to use a circle, a rectangle, and our trig equations, opposite equals hypotenuse times sine, and adjacent equals hypotenuse times cosine. This is so slick. Now, there are lots of ways to derive trig identities. In fact, Arthur Benjamin, in his book, The Magic of Math, he shows you how to derive it from a circle using cosine law and distance formula. There are lots of different ways. The one I want to show you today, I just find is so simple, and students find it really easy to play around and discover it themselves with very little intervention from the teacher, provided they're using the perspective opposite equals hypotenuse times sine and adjacent equals hypotenuse times cosine. Okay, here we go. Here's a little bit of information. The sum difference identities, as a math teacher, we all know them as called sum difference identities. To mathematicians, they're most commonly called, I'm showing you this book because this is one of the books that refers to them as Ptolemy's formulas. And mathematicians say they're most commonly known as Ptolemy's formulas. Funny how they're not commonly called that in high school math textbooks. So anyways, students, they're Ptolemy's formulas. Why? Because Ptolemy had to figure out a way to figure out exact half-chord lengths and distance from center in increments of half-degree movements. So he had to figure out more equations that would find relationships between sine and cosine so that he could find these exact values. So how do you do that? Well, you got to draw some more pictures. You can't just use the pictures we were using before because they gave us exact values for 45 degrees and 30 degrees. So mathematicians draw more pictures, use more geometry that they know, and see what kind of relationships they can come up with. So that's what we're going to do. All right, so Ptolemy's formulas. I'm going to draw in another angle B that isn't equal to angle A. Now you can draw it as equal to angle A. You end up getting a special rectangle called a square. So this time I just want it to not be a special rectangle. Now, this is our regular triangle that we label. The half chord length is also called sine A. I'm just going to highlight it in red because that's our special triangle inside our circle there. I want to look at another movement of angle B that's not equal to angle A. From there, I want to draw a rectangle that will circumscribe and contain all the important information in that picture, angle A, angle B, and the vertices of that red triangle. Here it is. So you can actually construct this. The students can draw this as well if they would like, and they can make angle A any size that they want, draw an angle B as a different measurement, use their compass and protractors to draw on the right angles, to draw on the rectangle. Here's your picture. From this picture, we can actually label all the sides in that new rectangle and discover Ptolemy's formulas just from this picture. All right. If you take away the circle, it's just a picture of a rectangle that has some line in it of length 1, and then draw on a right triangle that's circumscribed by that rectangle. Call that angle A. Opposite side is sine A. We'll know the adjacent side is cosine A. I kid you not, this is actually a picture out of a grade 12 math textbook where it was just a rectangle and it had some line 1 that started at a vertex and intersected one of the other side lengths of the rectangle. Draw on your right triangle, and you just know that one length has to be 1. They give no explanation as to why that length is 1, but when you go back through the history, it was 1 because it was 1 unit long in a circle. It was a radius. And high school teachers were trying to get students to just use the trig ratios to find the side lengths in the rectangle, and students were getting stuck and frustrated. So now that we've been showing students to use the trig equations opposite equals hypotenuse times sine and adjacent equals hypotenuse times cosine, using those formulas in that perspective, students found this so much easier to label the sides of the rectangle. So pause here now, give it a go if you would like to try it on your own, or follow along. We already have the triangle inside pretty much labeled because we know that adjacent side to angle A, that distance from center, is cosine A. Okay, so now we want to start labeling some of the sides in the rectangle. Well, in that bottom right triangle, we know the hypotenuse is cosine A. There's an angle B. So we can label the adjacent side to angle B. Remember, adjacent is hypotenuse times cosine B. So I labeled the picture, I labeled the hypotenuse in green so you can just see the formula. Adjacent side is hypotenuse cosine A times cosine B. And the opposite side is hypotenuse times sine B. Hopefully the color coordination helps you see it. Okay, so now we've got to travel around our rectangle here, fool around with some angles. If that red angle B is just B, can I find the other angle in the triangle? Sure, that's 90 minus B. We know that there's another right triangle in that blue square there, so can I find the measurement of the other angle? Sure, angles in a straight line add up to 180. Subtract the other two angles. You end up finding that other angle in the top right triangle is B. Now again, just use your formulas. Opposite equals hypotenuse times sine, adjacent is hypotenuse times cosine. Label those sides in that right triangle there. I highlighted the hypotenuse sine A in green so it would pop out in the side lengths. So the adjacent side is hypotenuse times cosine, sine times cos. The opposite side is hypotenuse times sine B. So hopefully the color coordinating helps you see the formulas. Now what we have is one more triangle to find the side lengths of so we can complete all the side lengths of the rectangle. So again, fool around with the angle measurements. If that's angle B, then the other angle has to be 90 minus B. In that triangle in the middle, we know where angle A is. The other one's 90, so the other one must be 90 minus A. Straight line equals 180 degrees. Subtract 90 minus A, subtract 90 minus B from that. Voila, you get that angle to be A plus B. Very cool. Now, the hypotenuse in that triangle is 1, so super easy to label opposite side as sine A plus B and adjacent side as cosine A plus B. All right, there you have it. So I encourage you to draw this picture yourself and do the math yourself so you can see how the formulas make it very easy to label the sides. Now we have elementary geometry here. It's a rectangle. Opposite sides in a rectangle are equal length. So all I have to do is set those math expressions equal to each other and voila, I got the sum difference identities. Oh, sorry. Ptolemy's formulas ready to go. And the cool thing is once we have Ptolemy's formulas, we have all the trig identities. We've done all the work to set the foundation for every trig identity that high school students usually have to study, know, play around with, do proofs from. And by having them derive the formulas and mess around with substitutions, they get the idea of how you play around with equations so proofs aren't so arduous to them. All right. So you did this all with a rectangle and these two formulas. This is why I think this approach is so beautiful for high school students. So the top side length of that rectangle is cosine A plus B plus sine A sine B, and it's equal to the other side cosine A cosine B. All you have to do is subtract sine A sine B from both sides of the equal sign to get the cos A plus B formula. The fun thing is most grade 12 students already have a formula sheet that has these formulas on it. So I think it's really fun to tell them, look, you're going to be able to figure out these formulas from this picture. Have at her. Start playing around with them. See if you can derive those formulas. See which formulas you can derive. It's more fun if you don't tell them which formulas they're going to derive, but that they are going to figure out some of the formulas on the formula sheet. So basically we get the foundation we need for every trig identity right here. I guess I just wrote them in the order of, like for cosine A plus B, I wrote them in the order where the first term is positive and the second one's negative. That's just some kind of textbook convention. You can actually write cos A plus B is equal to negative sine A sine B plus cos A cos B, whatever. All right. This is a great time to pause if you want. I'm going to have two handouts on James Tanton's G'day website for these videos, and the first one handout will just be so you can follow along and fill in the sides of the rectangle. The second one is going to be where you can follow along with the substitution or try the substitutions on your own to generate all the trig identities for, usually it's grade 12 trigonometry. All right, so if you're ready to play, let's play. Otherwise, pause, get the handout, take a break. Here we go. We have sine A plus B formula. Okay, so mathematicians just want to play around. What happens if I change one of those angles? All right, so once we are going to substitute in negative b for positive b, we get to use that cool picture where we drew in the triangle for angle A and knew the half-chord length was sine B, or sine A. And then if we reflected below the x-axis, because we did a negative angle rotation, we got the negative half-chord length. And we also looked at the distance from center. So if I rotated a positive degrees and a negative degrees, the distance from center would be exactly the same. So cosine negative b was exactly the same length as cosine b. So we're going to use these properties to fill in when we're doing our substitution. Let's give it a try so we can see what new equation we can come up with. All right, substitute in negative b. In our formula, instead of it being a plus b, it's going to turn into sine a minus b. So wherever you had sine b, that now becomes sine negative b, and cosine becomes cosine negative b. Well, cosine negative b and cosine b is the same distance from the center, so that just stays cosine b. And the sine negative b becomes negative sine b. It's multiplication, so you end up getting sine a minus b is negative cosine a sine b plus sine a sine b. Really, you're done there, but we know the convention is they want to have a positive term first in the expression and then the negative term. I don't know why. So if you need to rewrite it, fine. But this is really good for students to see that when they're deriving it, it might not look exactly like the formula on the formula sheet or in the textbook, but that's okay, because just because it doesn't look the same doesn't mean it's wrong. All right, let's try substituting for the other angle. Stick A in for B, see what happens. So then we have A plus A. You end up getting the same term repeated. That's one of the double angle formulas. Sine of 2A is 2 times cosine sine A. Let's play around with the cosine formula. Cosine A plus B. We can substitute negative B for B. Our formula becomes cosine A minus B. And then we just sine negative B becomes negative sine B. So we end up with cosine A cosine B minus sine A times minus sine B. Negative times negative is positive. Here we go. Cosine A minus B is cosine A cosine B plus sine A sine B. Yay! All right, you can substitute in B for A. I mean, this is where it's fun to let the students go and start substituting in different angles, positive and negative of each other, and just seeing what they come up with. We have to let the students go here a little bit. If they're just following us along, it gets really boring. If they play around with the substitutions and see which formulas they can come up with, it's a lot more interesting, it's a lot more satisfying for them, and they get that taste where, yes, in trig identities, it is about fooling around. We're just fooling around with the expressions and the equations, seeing what other equations we can come up with and see if they're true for all values of angle movement. All right, so let them play around. Put B in for A. You get cosine B plus B. We're going to get cos 2b, the double angle, is cos squared b minus sine squared b. Hey, that almost looks like Pythagorean theorem. That makes me think of the Pythagorean identity. Okay, so Pythagorean identity, I could substitute cos squared or sine squared and substitute it into the equation and see if I get another formula. So I would encourage the students to play around with that. You can isolate sine squared b and get 1 minus cos squared b. Substitute that in for sine squared b in the formula. See what other form of cos 2b you come up with. Cosine the double angle. And here's where they can substitute and play around and see what other formulas they get on the formula sheet. All right, math is not a spectator sport, so you can continue to play. We already know tan theta is equal to sine theta divided by cosine theta. We discovered that in the very first video that I did with you. It all came from the circle. So if we have tan double of an angle movement, remember it's just tan of any angle movement. So if I double the angle movement, it's still any angle movement. So that must equal sine of double the angle divided by cosine of double the angle. And you now have lots of different formulas for sine 2 theta and cosine 2 theta. So substitute them in, do a little simplifying, see if you can come up with a formula for tan double angle. Have fun in playing. Okay, so this is where, after I've had the students basically generate all the trig identities for themselves, we've usually covered like a whole chapter in some math textbook or a whole chapter in a math workbook. This is where you explore the whole concept of trig identities all together. It might take a couple of class periods to go through all the explorations, they generate them all. But the beauty is then for the next couple of classes, I get the students to cherry pick questions out of all the other sections and just try them out. Because now we can verify that these formulas work for all angle movements. They could be substituting in angle movements. They could be graphing them to find solutions. We are starting to mess around and have some fun with trig identities. So this approach of doing it all together versus teaching all the sections separate, where you would just like start off doing Pythagorean identity for one whole section and doing questions. And then you're going to do the double angle formulas. And then you're going to do the sum difference formulas, or whatever order you do it in. I don't know. Whenever it's so disjoint, it just makes trig identities so daunting and so boring. So I would encourage you to let them explore it all as one topic, do it all together in one class or two classes, and then now they have class time to try questions from all the sections, test their knowledge, and now you have a lot more class time to be working with students who need a little more support with playing around with it, or you can have a lot more classroom debate, have kids working in teams on the questions from the different sections and have more class debates about how would you do that? Oh my God, you solved it that way? Cool. Did anyone solve it a different way? And then you can be sharing your different proofs or your different math expressions of how you solve things, because that's what's fun about trig identities. There's more than one way to mess around with the equations. So have fun playing with this. Totally encourage you to do it all together, all the concepts in trig, and then play around with the sections. All right. If you want to learn more, I think I'm going to do one more video showing you how you can generate these also from the circle using the cosine law and the distance formula. But this is also like, let's say you've already had the students generate all the trig identities. This activity can be another awesome question that you just assign to groups and say, okay, let's play around with this picture. Let's try to figure out the distance in more than one way using two different formulas. Maybe we don't even tell them cosine law and distance formula and see if they can figure out which formulas they need to calculate the distance between 2 points on the circle and see if they come up with any identities on their trig formula sheet. All right, stay tuned for that one. Have a nice day.